Hello, this is lecture 15B for Calculus 1 using the fundamental theorem of calculus, part 2, to solve initial value problems where you can't compute the interval. In other words, in real life. My name is Scott Grizzard from the University of South Florida, and it's our last lecture for Calc 1. Makes me sad. Anyway, so what we want to do today is we want to look at how to solve these problems in real life. Because in real life, as opposed to the test where we just want to, solve it and get the answer. In real life, we're going to want to solve area under the curve problems, especially statistics, medicine, those sorts of things, where two things are true. One, we're okay with an approximation of some sort within, some significant digit. And the second thing that we're okay with is that we may not be able to have a perfectly good antiderivative for what we're looking for. Now, we're going to look at a problem today. Because I want to look at it conceptually, I'm going to pick one where we can do the antiderivative for it, a clean antiderivative. But that's not necessarily true in real life. You often wind up with things where you can't compute them, or you don't want to compute them because they're complicated. So let's look at this. This is another look at initial value problems. I've got this total cost curve, which is a function that will describe how much it costs to produce Q units of some good. And the marginal cost is given a level of output, the cost of producing one more. So we're looking at a forward-looking marginal cost. The marginal cost of producing that first unit is the marginal cost of zero, because the next unit after zero would be the first. Which is a little bit confusing, but we want that way so the math works out cleanly. You can make the math work out either way, but this way it's a little bit cleaner. The fixed costs are the cost the firm pays like rent, even if it produces no output. So the total cost of zero is going to be the fixed cost. So suppose the marginal cost of producing a gallon of Acme rocket fuel, it conforms to this equation. The marginal cost of Q equals 200 times 2Q plus 9 to the negative 0.5. And the firm's costs are 2,000. Now the question is, what's the total cost of producing X? What's the total cost of producing 100 gallons or 200 gallons or 500 gallons? So let's look at this from a slightly different perspective. So if I make my little, here's my little, let's look at this here. So here's a little Excel sheet I made up. Let me zoom in so you can see it. So here's my little Excel sheet. Here's my problem. And what I want to know, so on this side right here, what I put in for my formula here is the marginal cost. So I put in this formula here, and then I multiplied it by the margin. So I'm going to start with a margin of 5. Excuse me. Starting with a margin of 5, I'm going to compute the marginal cost of the next 5 units. So this is a per unit marginal cost. I'm going to have to multiply it by 5. And my fixed costs is in the problem are 2,000. Now, if I want to produce no units, of course, my total cost is 0. My total cost is 2,000 because that's what my fixed costs were. If I want to produce 5 units, what I want is the marginal cost of producing the next 5 units when I'm at 0. So I'm going to take the marginal cost at 0 and multiply by 5. I'm going to wind up with 333 simoleons, 0.3333 simoleons. So if I want the total cost of producing 5 units, I'm going to have 2,000 plus this unit here. Now, if I want to compute this one, here, let's go ahead and compute the marginal cost of 5 and multiply it by 5. So I have now the marginal cost, and you can look at this bar graph that I made down here. This right here was the marginal cost of producing 0 units. I had this 333.33 simoleons, and then I multiplied it by 5. So the area of this rectangle here represents the cost of the marginal cost of the 0 of this the marginal cost of producing the next 5 units if I'm not producing any, or the first 5 units. Likewise, this right here, this little rectangle, represents the marginal cost of producing the next 5. So it could go from 5 to 10. Okay. Well, in order to produce this right here, this number right here, I'm going to add this number, the total cost, plus the cost of producing 0, the first 5 units, 0 to 5, and then the marginal cost of producing the next 5. And the way I'm going to do that is I'm going to take this unit, I'm going to take the sum of this unit plus this plus the 2,000. So I'm going to take the sum of some C4 to C5. That's those 2 units, and I'm going to add them together, and then I'm going to add the fixed cost, which is that one in blue. And I'm going to hit enter, and that gives me the total cost of producing this, which is the area of this rectangle plus the area of that rectangle plus the 2,000. Okay. Well, let's go ahead and do another one. So I'm going to work this down. There's the marginal cost of producing the next 5 units. And because I've structured this in a certain way, oops, I went too many. This right here represents this cost plus this, and that. And that's my total cost. Well, as you can see, this pattern's going to hold. Let's go ahead and go out to 100 units. So if I add this rectangle, this rectangle, this rectangle, this rectangle, this rectangle, this is every 5 units, I'm computing the marginal cost, and then I'm multiplying by 5, which gives me the area of this particular rectangle. Okay? Now what I'm going to do is I'm going to add all those up plus the 2,000 to get my total cost at a particular point. So this formula right here represents taking 2,000 and adding up all the marginal costs that came before. Likewise, this formula right here is that 2,000 plus all the marginal costs that came before. Well, if I add those up, well, it looks a bit like a Riemann sum, doesn't it? Well, what happens if I take a margin of 1? If I take a margin of 1, this gets kind of large. But I can do the exact same formula, and I do a margin of 1. So instead of multiplying this by 5, which is how I got there, I'm going to multiply this by 1 each time. And my margin of 1, so I'm pricing by the gallon of rocket fuel, right? My total cost is going to be, for this one, is going to be this unit plus this unit. For this one, it's going to be these 2, right? The marginal cost of producing the first unit plus the marginal cost of producing the second unit, right? Which is the marginal cost of 0 plus the marginal cost of 1 plus the 2,000. Okay? And so on and so on and so forth. So what I'm doing is I'm adding all these rectangles and then adding the fixed cost, which was 2,000. Okay, well, there's no reason to do this at, why am I pricing at 1 gallon? What if I priced at half a gallon? And it's going to look like this. So I'm going to have more and more and more and more rectangles as I go on. In other words, what I wound up with was the Riemann sum, and I'm going to take the limit of the Riemann sum as I go to, as my margin goes to 0, or as my number of rectangles goes to infinity. Right? I could do the margin at 0.25. That would increase the rectangles by even more. So as I let change in Q go to 0, by making n go to infinity, I wind up with the Riemann integral. And that's the big idea. So you can see how I've worked this out. Right? These are these numbers that I just showed on the screen. So I have my fixed cost plus my sum of my marginal costs. And that corresponds to these rectangles. And then I could go by the half gallon. So I could go by the half gallon, and so on and so on and so forth. So what I wind up with here is that the total cost of Q equals the fixed cost plus the integral from 0 to Q of the marginal cost, which means that the total cost equals the total cost of Q equals the total cost of producing 0 plus, which is the fixed cost, plus the integral from 0 to Q mx. But if I move t of 0 to the other side, I get tq minus t of 0 equals the integral from 0 to Q of mx dx. But we have a term for that. That's the fundamental theorem of calculus, part 2. What is it doing there? Okay. Well, there you go. If I add all the rectangles and then I add the fixed cost, I get the total cost of Q. And that's the fundamental theorem of calculus, part 2, which is very nice. Now, because this particular problem has a clean antiderivative, I can do it the antiderivative way. So if I want to find the total cost, if the fixed cost is 2,000 and the marginal cost is equal to this, well, what I'm going to do is I'm going to take the antiderivative. I'm going to pull out that 200. It's just ugly. And I'm going to do the antiderivative here of 2q plus 9 to the negative 0.5. I'm going to let u equal 2q plus 9. That means that du over dq equals 2. Which means that dq equals du over 2. I sub that in here, and I wind up with 100. I do the antiderivative here. I pull out the 2, which makes that a 100. And then I'm going to wind up with this. I'm going to multiply, I'm going to add up 1, right? So I go from negative 0.5 to 0.5. And then I'm going to do 1 over that, which ends up being, this is the number 2. 1 over 0.5 is the number 2. So I wind up with 200u plus to the 0.5 plus c, and I wind up with this as my equation. All right, now I need to solve for my constant. So I've got t of 0 equals 2,000, which means that I'm going to wind up with 200 times 2,000 equals 200 times 2 times 0 plus 9 to the 0.5 plus c. Now I'm going to divide through by 200, do a little mathy, and I wind up with c over 200 equals 7. Multiply the 200 over there, and I wind up with a constant of 1,400. Okay? So this then becomes my equation for the t of q. And let's say I wanted to solve for t of 6. I would plug this into my calculator with a 6. I would wind up with 2,316.515151. Have fun. Okay. So that would be one way to solve this problem, and the perfect way you want to do it on the test. That's the way you want to do it on the test. There's a real-world way to do this, though, and that's the FTC way. And what I'm going to do is I'm going to take t of q equals t of 0 plus this integral. The integral from 0 to q of 200 times 2x plus 9 to the negative 0.5 dx. That is going to be the thing I plug in my computer. Sometimes I can't get a clean solution, but I can estimate this very nicely. Okay? And your computer will actually do this for you. So here I'm going to go ahead and go back into Maple, and I'm going to actually compute these things using the computer. So here I'm going to let this, here I chose 20 as my Q. And I'm going to go ahead and go all the way back to the beginning. And I'm using the trapezoidal method because I want to do, this is called the trapezoidal. I could have used something like the midpoint. Okay, here I'm using a midpoint rule to compute this. And then I'm just going to let this go in my Riemann sums, just like we did when we did Riemann sums. So what I'm going to wind out with when I compute this is I'm going to wind up with something that looks kind of close to 800. Here, if I did it, let's do it for the interval 0 to 6, because that's what we used before. And we want midpoints again. And I'm going to do midpoint, and the computer comes out with this fairly quickly, and it comes out with an answer of about 316, blah, 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 blah. Well, I take this 316 of this integral that my computer gave me, and I simply add, the t of 0, which was the 2000. And I came up with a number. And the computer, as I said, will do these integrals for you. Okay. Let's look at another example. Let's look at one where it actually comes out. Here, if I work it out, if I do 20, it's going to come out to a clean 800. But you can see here, using this midpoint method, I got 799, and I only used 512 intervals, by the way. I could have gone farther. It's going to take just a minute to compute those farther ones. There it goes. I could have gone farther. I could have used more intervals if I wanted something, and that wasn't horrible. Right? I could use 16,384 intervals, and I get 799.9999. It's within the digits that I wanted. Right? So I wind up with an answer. If I plug in 20 and I let it solve it numerically, I wind up with something that's a rounding error. That's a very, very, very small number rounding error off this thing. And remember, I can make this error arbitrarily small. Okay. If I actually ask the computer to compute that integral to 20, I'm going to get, and the computer will symbolically solve this one, because remember, I chose one that could be done either way. And because I did that, I wound up wind up with a solution of 800. And indeed, this thing, well, if I give this an X in here, it will solve this thing symbolically for me. Right? There's my antiderivative answer, according to the computer. That's the interval from 0 to x, and then I need to add. It's off because I need to add the 200. I'm sorry, the initial cost, if you remember. Let's do that. Right, so if I do the interval and then I add the 2000, I get back to what I had when I did it the antiderivative way. Right, this and this are the same numbers. Okay, so that's the other way to do these problems. There's a different way. You could solve these things with the clean solution, where you do a nice, you do it with and this is that antiderivative, by the way. That's this thing right here, is this, what the computer just did right here. That's this worked out. So I could solve it that way. However, I can't always find the clean solutions. So in real life, what you can do is you could set up this integral, right, to what you want to solve. So I could set up this interval with t0. I add my 2000, and then I do my integral on the computer. Or on one of these band calculators that have the integral signs, the scientific calculators, those will actually do the numeric integrations for you. So if you're looking to calculate areas under the curve in real life, you can use your calculator to do it. And then you just add the initial cost or the initial value. So there is another way to solve these initial value problems. Okay, well, that is it for the class. It's been exciting getting to know a couple of you through comments, and getting to know a couple of you, and getting to know those of you who are taking the class live at USF in person. Uh, I will see you then. For those of you that are in the class, I will see you during the class this week and for the final exam. Thank you very much for watching, and I will see you later.